Unit 4, Chemical Reactions. In this part, we're going to cover a series of reactions: combination reactions, combustion reactions, decomposition, and single replacement, often called simple replacement. In combination reactions, there are three types we will discuss: metals and nonmetals, metal oxides with water, and nonmetal oxides. When we predict reactions between metals and nonmetals, one of the things that we have to do is we have to know the oxidation numbers of these elements, the common oxidation numbers, in order to complete the equation. For example, if we have magnesium reacting with oxygen, magnesium possibly burning an oxygen, we're going to produce a compound we expect of magnesium and oxygen. But is this the correct formula? Well, the oxidation number of magnesium is expected to be a +2, and of oxygen is expected to be a -2. So it looks to me as if this formula is right because it's neutral. The +2 and the -2 cancel. But is it balanced? Now, I want you to pay attention to something, and this is very important. Do not balance the equation until you have finished writing it. And we're through writing it, so let's balance it. Well, we have one magnesium on the left and one magnesium on the right. That looks good. But we have two oxygens on the left and one on the right. So we need two oxygens over here, which means then that we have two magnesiums. So we have to put a 2 here. Get the idea? We'll try this one for size. Here's aluminum plus chlorine. Now, we'll write them down, aluminum and chlorine. What is the oxidation state for aluminum, the common one? It's +3. And for chlorine, it's -1. So in order to make this be the proper formula, we have to have 3 chlorines. And there we go. Now let's balance the equation. Well, let's see. I have one aluminum and one aluminum. That looks good. But I have 3 chlorines on the right and 2 chlorines on the left. Oops. What's the least common multiple of 3 and 2? And the answer is 6. So I need to put a 3 in front of chlorine to make it 6 chlorines, and a 2 over here to make this 6 chlorines over here. Now chlorines are balanced, but we screwed up aluminum. So throw a 2 over on the left. And there you go. Now try this one. A compound of calcium and nitrogen. Take a second, look at it, figure it out, and write the formula down. What I figured is the formula is going to be Ca3N2 to make it electronically neutral. We have 3 calciums on the right and only 1 calcium on the left, so I need to put a 3 here. And oh, guess what? It's balanced. Got the idea? There's an interesting reaction series when your alkali metals react with oxygen. You can form oxides, peroxides, and superoxides. Let's look at this. If you have lithium reacting with oxygen, it tends to form lithium oxide, Li2O, just a straight oxide as you would expect. However, if you take sodium plus oxygen, you may find yourself producing sodium peroxide, Na2O2, in which the oxygen has a -1 charge, or is recorded as having a -1 charge instead of a -2. But look at this. Potassium plus oxygen produces KO2. This is called a superoxide. What is the oxidation state of oxygen in this? Well, if we assign potassium a +1, then oxygen will have an oxidation state of -1/2. Rubidium plus oxygen, see, we're still going down the family of the alkali metals, will produce also a superoxide, RbO2. What do you think cesium and francium might do, the last two? Well, if it follows this trend, then they will form superoxides. The larger alkali metals tend to form superoxides. Just an interesting little item you should have tucked in your pocket. Metal oxides with water. Now, metal oxides tend to react with water to produce bases or hydroxides. For example, we have magnesium oxide. The product may be of magnesium burning in oxygen, dissolving in water to produce magnesium hydroxide. Now, folks, look at that. Is it balanced? Yes, it is. But remember, don't balance the equation until you've finished writing it. What about aluminum oxide plus water? Well, aluminum oxide plus water likewise should form the hydroxide, aluminum hydroxide. And we balance this equation. Let's see. 2 aluminums on the left, 1 on the right. We need a 2 here. Then to balance oxygen, we're going to need a 3 here, and hydrogen checks. Okay, good. Let's go on. Nonmetal oxides with water may be a little more challenging. Nonmetal oxides react with water to produce acids. Well, that kind of makes sense, doesn't it? After all, metal oxides react with water to produce bases. Well, let's look at some examples. Sulfur dioxide plus water will produce sulfurous acid. Okay. Sulfur trioxide plus water will produce sulfuric acid. Okay. Cl2O3 plus water produces chlorous acid. Well, at first glance, it may look quite simple, but how can you predict? Well, there are 2 ways to predict. Let's look at these. Let's look at this reaction. We have N2O3 dissolving in water, and the question is, what's it going to form? Well, ask yourself the question, what radicals of nitrogen and oxygen am I familiar with? And what acids are associated with those radicals, or polyatomic ions? Well, we're familiar with HNO2 and HNO3. HNO2, which is related to the nitrite radical, and HNO3, which is related to the nitrate radical. So how do we know which one of these is going to be produced? Well, what we do is determine the oxidation number of nitrogen in each of these acids. Nitrogen is your key. In the HNO2, now nitrogen is the middle element. Do you remember how to do this? The nitrogen is going to have an oxidation state of +3. And in the nitric acid, the nitrogen will have an oxidation state of +5. Now the question to ask is, which of those 2 acids has the same oxidation number as the nitrogen in the nonmetallic oxide? Well, in the nonmetallic oxide, N2O3, oxygen is a -2, that's -6. Nitrogen has to be a total of +6, but there are 2 of them, so each nitrogen has a +3. So that then is associated with the HNO2. Therefore, this acid is the one that is formed from this oxide. Do you get the idea? Cl2O3 plus H2O is going to produce an acid containing hydrogen, chlorine, and oxygen. But do you remember that there are 4 of those? Let's see, there's the HClO, the hypochlorous acid, from the hypochlorite radical. And there is HClO2, chlorous acid, from the chlorite radical. There is HClO3, chloric acid, from the chlorate radical, and there is HClO4, perchloric acid, from the perchlorate radical. The question is, which one are we going to get here? Well, what we have to do is find these oxidation numbers. The oxidation number of chlorine in the first one is a +1. Figure the oxidation state of chlorine in the second one. And do you get that it is a +3? And in the next one, the oxidation state of chlorine is +5. Figure the 1 for the perchloric acid, and it is +7. So now what we have to do is find the oxidation of number of chlorine in the oxide, right over here. So figure it out. And when you do this, you will find that the oxidation state of chlorine is +3. Well, if it's +3, what does that coincide with? That tells us that this right here is going to produce this acid right here. So because the chlorines have the same oxidation state in both. So our equation becomes Cl2O3 plus H2O produces H. We'll try these. What if you have P2O3 plus H2O? What are you going to produce? You might want to stop this video or stop this program for just a minute and try your hand at this one and then come back and have a look at it. And I'm getting ready to tell you how it works. The oxides that I'm familiar with will produce the acids H3PO3 and H3PO4 based on that table of common oxidation numbers that we gave you earlier in this course. The oxidation state of phosphorus is a +3 here, and what is it in the second? It is a +5. What is the oxidation state of phosphorus in the oxide? It's a +3. Therefore, the acid that I would expect to be formed is the H3PO3, phosphorus acid. Now let's do the same thing with this one. Here we have AS2O5 plus water. You figure it out. If you want to, stop this program for a moment, figure it out, and then start it back up again. There are two acids with which I would think we need to consider. H3ASO3, arsenous acid, and H3ASO4, arsenic acid. Well, in the arsenous acid, the arsenous has an oxidation state of +3. And in the arsenic acid, it has an oxidation state of +5. What is the oxidation state of arsenic in the oxide? It is a +5. Therefore, the acid that we would expect to be formed would be H3ASO4, arsenic acid. Got the idea? Okay, now that you're probably getting kind of comfortable with that, let's look at it from a different angle. Let's go backwards, which will always also tell us a little bit of a different way we can go forwards. What nonmetallic oxide should be dissolved in water to form H3PO4? All right, you can go through and do oxidation states and figure the answer just fine, but there's a little bit of a different way you might find interesting. Make sure you have an even number of hydrogens. Well, one molecule of that acid, H3PO4, is odd, so we'd have to have 2 molecules. Got it? Now, how many hydrogens do we have in all there? We have 6 in all. And I want you to take out as much water as you can, making sure you remove all of the hydrogens. Well, you've got 6 hydrogens, so you can take out 3 waters. That means you can take out 3 of those oxygens. So, we've got the 6 hydrogens. Let's take out the corresponding quantity of oxygen needed, which would be 3. So we knock out this and leave us 1 from these 4. Plus we have 4 from the other one, so that gives us a total of 5 oxygens. What do we have left here? We have P2O5. Yeah, P2O5. That's the oxide that I need. Do you like doing it that way? Well, it's up to you. P2O5 plus H2O produces H3PO4. Now your oxidation states will check, or you can do it this way that I showed you. It's time for you to try some. What nonmetal oxides should be dissolved in water to produce these acids? Let's start with HNO3. Go through and get rid of your hydrogen and oxygen and determine what oxide you're left with. And you find you're left with N2O5. Got the idea? Oh, here's an easy one. H2CO3. It's so easy when you have an even number of hydrogens. Take out 2 hydrogens, take out 1 oxygen. What's left? CO2. What about this one? What do you have? SO3 plus H2O? Sure. That will produce H2SO4. Well, what about HiO4? Now, keep the faith. Give it a try. I2O7 plus H2O yields HiO4. Are you getting the idea? Non-metallic oxides with water produce acids. Metallic oxides with water produce bases. What if there were an industrial facility in your area that was producing large volumes of a gas consisting of non-metallic oxides, perhaps sulfur dioxide, such as might be emitted from a paper mill? What would be your thinking regarding this? Would you dislike the stench? Would you say it was the odor of money? What would be your comment? And then, when that sulfur dioxide is exposed to air, what happens? Think of sulfur dioxide reacting with oxygen. And what does it produce? Sulfur trioxide. Now you have the sharp choking fumes of sulfur trioxide. Along comes a cloudy day, and it rains. Do you think, oh good, it's raining, it's going to wash this mess out of the air? Or do you think in terms of, uh-oh, sulfur trioxide and water? And what does it produce? That's right, sulfuric acid. And then you're raining sulfuric acid, although perhaps pretty dilute. But what about the things in your environment? What about the things you may treasure? What about a piece of marble statuary? What about the concrete columns in some of the buildings? What about your automobile? How do these things react when exposed to sulfuric acid? It behooves you as good citizens to understand some of this that's going on and know why it is so important that industrial facilities, for example, take such care to clean up the things that they are putting into the environment, whether it be into the air or into the water. That's right. Chemistry will help you be a better citizen. Let's consider combustion reactions. Now, what are they? Well, combustion reactions are reactions that are accompanied by the evolution of heat and light. Notice we didn't say anything about oxygen, did we? Does that mean that oxygen is always involved or not? No. Oxygen is not always involved in combustion reactions. You can have combustion occurring in other mediums. But for our purposes, we are going to consider combustion and oxygen. But remember, technically, combustion reactions are reactions that are accompanied by the evolution of heat and light. When a metal undergoes combustion, have it go to its maximum oxidation state, unless something tells you otherwise. Now remember, this is combustion and oxygen. For example, suppose we burn iron and oxygen. Now what is the maximum common oxidation state of iron? Yeah, it's a +3. So when it reacts then, you can expect it to form Fe2O3. And with magnesium and oxygen, you would expect it to form MgO. Yes, you're saying, but wait a minute, we just studied those in combination. Okay, so this is an example of combination reactions which are in fact combustion. Now let's look at nonmetals. When you're talking about combustion reactions involving nonmetals, have the nonmetals go to the dioxide unless something else is giving you indication of otherwise. Now remember, this is combustion and oxygen. So for example, you might use carbon plus oxygen. We'll write it as carbon dioxide unless something tells you differently. Sulfur and oxygen, have it go to sulfur dioxide again, unless something tells you differently. And here's an example. Consider limited oxygen. If you have carbon with limited oxygen, see, that's telling you something other than having it go to the dioxide. What is a lesser state that you can go to with carbon? You can go to the monoxide. When compounds undergo combustion, have each element behave as if it were not in a molecule. In other words, consider each element and its reaction with oxygen. For example, suppose we start with methane, CH4 plus oxygen. The carbon reacts with oxygen producing, that's right, CO2. The hydrogen reacts with oxygen producing, that's right, H2O. So there are our products. Now try this one. C2H6S plus oxygen. The carbon produces, the hydrogen produces, the sulfur produces, and so you get this. Carbon dioxide plus water plus sulfur dioxide. What if you had zinc acetate and oxygen? Well, what's the zinc going to form? What's the carbon going to form? And what's the hydrogen going to form? That's right. It's going to form zinc oxide, carbon dioxide, and water. Now you say, but what about the oxygen? Well, the oxygen that's from the acetate and the oxygen that is coming from whatever source of oxygen all combine to produce these three compounds. But what if you're dealing with something like this? Sulfur dioxide plus oxygen, that gives us sulfur trioxide. But now look at this. Carbon dioxide plus oxygen gives us no reaction. Also, if you look at this one, zinc oxide plus oxygen, that likewise gives us no reaction. However, manganese oxide plus oxygen produces MnO2, among other things. How do you know? Why does it work this way? The time has come to learn about something we call, or that we're going to call, the range of oxidation states. All right, look at your periodic table. Let's show you some oxidation state trends. Got it? Got your periodic table handy? All right, let's look. Over here in the 1A family, let's look there first. The range of oxidation states, of common oxidation states, or the range of oxidation states, is 0 to +1. So, hydrogen is not really in that group. Lithium, sodium, potassium, rubidium, cesium, and francium. Either a 0 or a +1. In the 2A family, it's 0 to +2. Okay, what about, let's go over to the 3A family, over with boron. That's 0 to +3. Let's look at the carbon family. That's -4 to +4. That means -4, -3, -2, -1, 0, +1, +2, +3, and +4. Let's look at the nitrogen family. That's -3 to +5. -3, -2, -1, etc. Let's look at the oxygen family. What do you surmise? -2 to +6. What about the halogens? -1 to +7. Yeah. Well, let's look at the transition elements. Let's start down there with the scandium bunch. It's 0 to a +3. The titanium family is 0 to a positive 4. Don't start assuming something just yet. 0 to plus 5 for the vanadium, 0 to plus 6 for the chromium. The manganese family is 0 to plus 7. And the rest of these are varied. But these we can determine the range of oxidation states pretty well. But these others just have too much of a variety, and those you're going to have to consider individually. Got that? Using this information then, that periodic table with the range of oxidation states, can you see that as a way of helping you predict why carbon dioxide and oxygen would not produce carbon trioxide, but sulfur dioxide and oxygen would produce sulfur trioxide? Well, let's go on. This next group of reactions is going to be decomposition reactions. And we're going to look at a series of decomposition reactions and give you a set of rules to help you remember so that you can predict what the reaction products will be. We're going to look at decomposition of carbonates, bicarbonates, nitrates, halates, and peroxides. Starting with the decomposition of carbonates. Now, metal carbonates decompose when heated to produce metal oxides and carbon dioxide. That's what they tend to produce. For example, if you take calcium carbonate and heat it, you should produce calcium oxide and carbon dioxide. Well, what about aluminum carbonate? You would predict that aluminum carbonate would form aluminum oxide and carbon dioxide. Got the idea? So that your carbonates then in heating will decompose to produce the oxides and carbon dioxide. Now there's something you need to know. Alkali metal carbonates do not react like this. Sodium carbonate, when heated, for your purposes will give you no reaction. I'm not going to say what would happen if you put a blowtorch to it. I'm telling you under normal heating circumstances, the carbonates, the alkali metal carbonates, do not decompose this way. Decomposition of bicarbonates. Metal bicarbonates decompose when heated to produce metal carbonates, carbon dioxide, and water. Now you have to be careful not to overheat. For example, by the way, it is important that you know that bicarbonates, well, they're really only, for our purposes, 1A bicarbonates, the alkali metal bicarbonates. For example, if you have sodium bicarbonate and you heat that, it's going to produce sodium carbonate, carbon dioxide, and water. That's right. Potassium bicarbonate on heating produces potassium carbonate, carbon dioxide, and water. Well, what about calcium bicarbonate? Oh no now, folks, don't fall into that trap. For all practical purposes, there are only 1A bicarbonates. Decomposition of nitrates. Your metal nitrates decompose when heated, now this is when heated reasonably, producing metal oxides, oxygen, and nitrogen dioxide. Metal nitrates decompose producing metal oxides, oxygen gas, and nitrogen dioxide. For example, if you take cupric nitrate and heat it, you will produce that black residue of cupric oxide, and you will produce oxygen gas and nitrogen dioxide gas. Would this be a good way to produce oxygen for use in the lab? Well, no. And the reason it wouldn't is you'd be producing nitrogen dioxide too, which would contaminate it. Oh well. What about aluminum nitrate? When heating aluminum nitrate, you should have produced aluminum oxide, oxygen gas, and nitrogen dioxide. Got that? Metal nitrates tend to produce metal oxides, oxygen, and nitrogen dioxide. Now, folks, you're not going to like this, but that's the way it is. Alkali metal nitrates react differently. That's right. Your alkali metal nitrates produce nitrites and oxygen. Again, we're not taking a blowtorch to it. Sodium nitrate, when heated, gently heated, will produce sodium nitrite and oxygen. Now, this would be a good way to produce oxygen for use in the lab. But don't overheat it, or you will produce something that you don't want. So sodium nitrate will produce sodium nitrite and oxygen. Decomposition of halates. Metal halates decompose when heated, producing metal halides and oxygen. Well, what are halates? Well, let me give you some examples. Here's potassium chlorate, sodium iodate, and calcium bromate. So they are the iodates, the chlorates, and the bromates. Now, in our imagination, we might imagine that they are fluorates also, but we're going to deal with these. Potassium chlorate, when heated, is going to give you potassium chloride and oxygen. You'd have to go back and balance the equation, and I will leave that up to you. Sodium iodate, when heated, will produce sodium iodide and oxygen. Calcium bromate, when heated, produces calcium bromide and oxygen. Got the idea? We'll get those down. The chlorates produce the chlorides, the iodates produce the iodides, and the bromates produce the bromides. And, of course, oxygen. Decomposition of peroxides. Now, there are 3 peroxides and their reactions that you are expected to know. Let's start with hydrogen peroxide. You may have noticed hydrogen peroxide is kept in a brown bottle, and the instructions very often are to keep it in a cool place. The reason is if it's warmed or left open and exposed to air, or if you put it on an open wound where there are certain enzymes, it will decompose to produce water and oxygen. Another peroxide is barium peroxide. Take barium peroxide, warm it a little bit, and you will produce barium oxide and oxygen. Or take some pellets of sodium peroxide and put them in water. Now, this is a different reaction. But when they're put in water and gently warmed, you will produce sodium hydroxide and oxygen. Now you've got all these decomposition reactions. How are you going to learn them? Use flashcards. Just put some of these reactions on flashcards and carry them with you. And spend about 2 minutes a day looking at them and saying them out loud, and you'll be amazed how quickly you will learn them. Simple replacement reactions. For simple replacement reactions, you're going to need an activity series like this. Now, this different activity series will have different elements on it. This is a fairly good activity series here. But here is how it works. An element will replace an ion below it. An element will replace an ion below it. But an element will not replace an ion above it. Give you an example. Here's a reaction of zinc. Okay, here's zinc right here. See it on the activity series? We're going to put that with cadmium chloride. Now, the ion that I'm talking about is the cadmium ion in this compound. And here's cadmium on the table. Now, is the element above the ion? And the answer is yes. Then a reaction should occur, and you should get zinc chloride and cadmium. You're going to have to know your oxidation states here. Copper. Okay, here's copper plus silver nitrate. Where's silver? There's silver. Will you get a reaction? You will if the element copper is above the ion silver in the compound. And the answer is yes, it is. So yes, you should get a reaction. And you will produce cupric nitrate and silver. Well, what about magnesium? Here's magnesium and hydrochloric acid. Should it react? Well, what's the ion here? It's hydrogen, and there it is. Is it above it? Yes. So what should the reaction be? It should be MgCl2 and hydrogen gas. Well, what about silver if I were to put it in hydrochloric acid? Well, there's your silver plus HCl. There's your hydrogen. Is the metal or the element above the ion? No, it isn't. Therefore, I should get no reaction. Get the idea? The element must be above the ion that's in the compound for the reaction to occur. If the element is below the ion, then for our purposes, no reaction occurs. What about aluminum chloride? And there's aluminum up there. But you notice I have the little green arrow? That's because that's the ion, isn't it? That's right. Aluminum is in the ionic state here, plus nickel, which is the element. And where's nickel? There's nickel. All right, is the element above the ion? So it doesn't matter what order you write it in. You always have to ask yourself the question, is the element above the ion? And in this case, it is not. Therefore, we should get no reaction. Well, folks, we've covered a lot of reactions. We talked about combination reactions, in which we combine either two elements or possibly two compounds to form a third. We talked about combustion reactions, and if you thought that combustion reactions looked very similar to combination reactions, you're right. Decomposition reactions. We talked about 5 different specific decomposition reaction types, and you need to know those. The decomposition of carbonates, of bicarbonates, of nitrates, of halates, and of a particular series of peroxides. We also talked about simple replacement reactions or single replacement reactions. And for this, you will need an activity series, or you will need to commit an activity series to memory. Chemistry. A better way to teach and learn chemistry.